Okay, so let me just. Okay, so today I will talk about dark matter production during reheating, because in some models, dark matter models, this reheating process in the early universe, either the inflationary reheating or any intermediate reheating period would affect the production of dark matter, the final relic abundance. So this is something that I've been working on since my PhD in Paris-Saclay. And I developed codes to compute this, the dark matter production during reheating, so the EVO EMD code. And also, I'll talk about the relic abundance in a little bit more detail, because at the time that I started working with Freezine, there were no numerical code, public code, to compute the Freezine production. So I had to develop my own codes. So this is what I'm going to share today. So basically, so this is the outline. So I would just split this talk in these two parts. So let's start with the reheating process in the early universe. So the expansion and the curvature of the universe is determined by the energetic content. Can you hear me okay? Or I don't know if it's... Yeah, maybe. So basically, we have the Hubble expansion, which is a function of time, this homogeneous expansion of the universe, and also the curvature of the universe is determined by the energetic content. So we have this is the Friedmann equation coming from GR. And this is the total energy density of the universe. For a flat universe, we have, when the total energy density of the universe is equal to some critical density, then the universe is flat. And this is what we observe today, so we will just, neglect the curvature of the space-time, and this is how the expansion rate is determined by the energetic content. So a relic abundance of a species K, let's say, is defined as the fraction among the energy density of this species, which is a function of time, and this critical energy, okay, which is also a function of time. So, and the total abundance, the total energetic content of the universe changes with time. Sorry, this is the total. So basically, we can have a contribution from the inflaton field that drives the inflationary period in the early universe. Just they start with the radiation content. We can also have the ultra-relativistic species, so the radiation content, the dark matter abundance also, and so on. So this is what I would talk today, the coupled evolution of the inflaton, radiation, and the dark matter content, okay? So the evolution, so I said that this, the components change with time as the universe expands. So the evolution of a species K, let's see here, in the phase space, is determined by the Boltzmann equation. So basically, we have the Liouville operator acting on the distribution function of the species K, and this is equal to the total amount of collisions, so the net collisions that this species can feel. So basically, all the processes that are producing and all the processes that are depleting the total number of this species K will change the way that they evolve in the phase space. So if we don't have collision, the particles only follow the geodesics and so on. But If yeah, if the net collision is zero, if the particles are produced and annihilated at same rates, this is. No, it's quantum. So all the processes that all the interactions that the particle feels. So this. Okay. Okay. All the interactions. It will be clear at some point that, for example, this will be like the cross section and so on, the K widths. Yes, the quantum collisions, the quantum interactions, non-gravitational interactions goes there. So all the interactions, so all the annihilation processes, N to M. It's quite general. So basically, you can have decays, inverse decays. You can have 2-to-2 processes, 2-to-3, and so on. So all the kinds of, all the possible interactions, non-gravitational interactions, contributes to this collision term here. So this collision operator. And I can define later, but it's basically. Because it's like a quantum, so the gravitational interaction comes from the geometry of the space-time in this case. But if you have like quantum gravity, so we can also have this. So, yes, but I mean, here we have the quantum amplitude for a given process. Yes. Yeah. So basically, so for a homogeneous and isotropic universe, the distribution function will be only a function of time and the absolute value of the momentum. So basically, we have the 4 momentum of this particle is the energy and the 3 momentum, and this is the absolute value of the 3 momentum. So because it's like a homogeneous and isotropic distribution of matter that leads to a homogeneous isotropic space-time. Okay, so basically this Liouville operator in this context of a homogeneous and isotropic universe would be basically the variation of the distribution function over time minus the Hubble expansion rate, the absolute value of the momentum, and how they change with momentum. So this is the Fk. So this will be equal to the collision operator over the energy of this particle K. So this is the Boltzmann equation, and this is a microscopic description of the problem. But if we integrate this equation, the Boltzmann equation, so I will put here. If we integrate the Boltzmann equation over the momentum, over all the possible states in phase space, so basically we have this integration over all the possible 3 momentum of the Boltzmann equation. Yeah, sure. Okay, so I'm talking about, so I'll just do a quick recap. Basically, I'm saying that the expansion of the universe depends on the energetic content, and the total energetic content have different components. So we have the inflaton, radiation, dark matter, and I'm talking about how these contributions, the different species evolve in phase space. So basically, we have the Boltzmann equation that relates the Liouville operator, so how the particles change like over the geodesic and so on. And this is the distribution function, or the occupation number, of this given species K. And this is the collision operator. So it's basically an integration over all the how to say, the momentum of all the particles that interact with this particle K. So yes, and yeah, this is the Liouville. Sorry. Fk is the distribution function of this species K. That could be the inflaton, could be the radiation. This is like a general, the general case. Like if we follow the evolution of any of the components of the universe, this is described by the Boltzmann equation. And this is the collision operator that depends on all the particles that interact with Fk that we are studying. And in a homogeneous and isotropic universe, the Liouville operator is just this. It's this times the energy of the particle. Okay. Sorry, yeah, you missed. So this is the Hubble expansion rate and the absolute value of momentum. Because the L, the Liouville operator, is defined as the change of the distribution function over this affine parameter. Okay, so since the distribution function depends only on time and the momentum, the absolute value of the momentum, then we can do the computations and come to this. Sorry, yeah. So this is H, the Hubble expansion rate. This is the absolute value of the momentum. Yes. Yes, yeah. Yes. Yes. Mm-hmm. So on shell. Yes. Mm-hmm. Yes, the Liouville operator for this homogeneous isotropic universe is this times the energy. Mm-hmm. So basically, if we integrate over the phase space, over the all the states, all the momenta that are possible for this particle K, this species K, we integrate and we find the following equation: the time variation of the number density of this species K plus 3h number density is equal to collision term, which depends on time. Now, by doing this, I'm defining the number density of this species as the total degrees of freedom, the internal degrees of freedom of this species. This factor here that comes from this integration as sum going to the continuum and so on in the phase space, in a quantum phase space. The momentum, let's see, it's just this. Integration over the distribution function. Okay, so this is the definition of the number density. And also we have the, the collision term. That is just the integration over the collision term itself. Okay, so this is a thermodynamic description of this of the evolution of this species K. Okay, and we can do kind of the same thing. Let me do here. We can integrate over the Boltzmann equation times the energy density. Okay, so we integrate this Boltzmann equation, the microscopic description, and we find how the energy is transferred in this system. So basically we have the energy density, in this case, of the species K, plus 3 times the Hubble expansion rate, the energy density of K, plus the pressure that I will just define right now. This is equal to the, let's say, a source term of that affects this, the energy transfer of this species here. So basically, the energy density is defined as oops, like this. So it's like an average, an average of the energy of the species. And we have also the pressure, which is the momentum flux. So the pressure will be just like this. The square of the momentum over 3 times the energy. Okay, and the distribution function. And we have the source term that is, again, just the, let me write it like this fancy R. This source term will be only the integration over the collision term, just like this. Okay, so if we use the first law of thermodynamics, then we can find, so the first law implies that this source term here, is equal to the temperature of this bath over the volume, and the time variation of the total entropy in a co-moving volume. Okay, so this will be very important to us because the reheating process will be a production of entropy in a co-moving volume. So if we have thermodynamic equilibrium, then that means that this is the Boltzmann equation, Boltzmann fluid equation for the number density. If we have chemical equilibrium, it means that the number changing interactions will be 0. So we don't have any change of the total number of the particles. And then this is the chemical equilibrium. So this collision term here will be 0. And if we have also kinetic equilibrium, it means that there is no source term. So it means that the entropy is constant, and that means that the interactions, for example, scattering, elastic scatterings, are changing, the particles are changing momentum, and they achieve a given temperature. But if we have kinetic equilibrium, then we just have, if we have, both chemical and kinetic equilibrium, we have the thermodynamic equilibrium. Okay? So now, let me just go here. Any questions for a moment? We'll see. Okay. So basically, what we have done right now was like to establish how to quantify the evolution of the particles as they interact. Oh, I shouldn't. No, yes, it's okay. Let me just leave this here, just in case. So this is Boltzmann fluid equation. We are just defining like a thermal bath. And I will just right now define what we mean by radiation and matter. So basically, radiation it means that the momentum of the particle is much above, it's much higher than the mass of this particle. And in this limit, we have the number density of radiation of this species K would be just proportional to the degrees of freedom of this species and T cube. Okay, and the energy density will be only proportional to the degrees of freedom times T to the 4, and the pressure will be basically equal to 1/3 of the energy density. Okay, so basically this is what we the limit case for radiation, and for matter we have basically, so that means the opposite situation. So when the momentum of the particle is much below the mass in this limit case, so the number density of this species for non-relativistic species will be basically, how to say, well, I just put the proportionality. So the degrees of freedom, the mass of the particle times temperature, 3 to the 2, and an exponential of minus the mass over temperature. So this is the Boltzmann suppression. So once the particle becomes non-relativistic, so once the temperature of the universe drops below the mass of the particle, the number density of the particle goes down. It gets suppressed. And the energy density will be just the mass, just the mass of the particle times the number density, which is also Boltzmann suppressed, so for the matter. And the pressure will be much below, smaller than the energy density. So basically, this is a pressureless field.
Sorry, are you assuming that everything is homogeneous? Is that the point? Am I missing something?
Yes. Yes, I'm talking about just a homogeneous.
And is that a good approximation?
Yes, we can have like the perturbations of this homogeneous situation, but for now, for our purposes, we just need a homogeneous universe.
So I understand, but so that's a big approximation, right? So nothing depends on where it is in the universe, right?
No, it's homogeneous isotropic.
And that's supposed to be valid until what? Just in the early universe, or is that supposed to?
Throughout the expansion, but
sorry?
Throughout the expansion. But if you want to
No, but now you have galaxies and things like that. So
yes. So yeah, before this is just for the dark matter production, before like BBN, before CMB release, and so on.
Okay, and there's strong evidence that this approximation is valid in the early universe.
We have evidence that, so because of the CMB, we have evidence that we were in a thermoequilibrium situation. So the anisotropies of the CMB, the difference in the distribution of the matter was very small.
So this is after CMB, sorry, I'm not.
Before.
This is before CMB. So,
yes.
So is it, so how is CMB useful in this?
So the CMB is a decoupling of the photon.
Right, but before the CMB, do we have evidence that the thing was homogeneous?
Before the BBN, we don't have, well.
I'm just trying to understand if this is a ansatz or if this is based on some experimental.
Well, the BBN assumes this homogeneous expansion, and this
BBN means what?
Sorry, Big Bang nucleosynthesis. The synthesis of the light elements assumes this for in the case of a radiation dominated universe, and this is well described, and it agrees well with the observations. Okay. So it's a. But before BBN, we don't have evidence, pretty much, about the universe. Yes.
But doesn't the relative isotropy of the CMB indicate something about this?
Sorry.
Whether this approximate, the CMB is roughly the same temperature everywhere, right? So doesn't that weigh in on this question?
Oh, yes. Yeah. But it's after the CMB, yeah.
Sorry, but doesn't the CMB itself is when the temperature was released when the temperature was about a third of an EV, and at that point, don't we know something about the universe at that point?
Yes, so it's
We know that it was
basically
very homogeneous,
anisotropy.
right?
Yes, homogeneous, and yes. The anisotropies are very, very, very small.
Okay, so this is at the same time or similar time to CMB. That was my.
So this is okay. So this is would be valid from much before, like for the inflaton.
Okay, so that needs BBN or whatever.
Yes.
Okay, thanks.
Very before.
But isn't it unlikely / impossible for the universe to have been very inhomogeneous much before the CMB and then magically become homogeneous at the time of the CMB? So isn't it much more likely that the universe was homogeneous throughout the whole time?
Sorry, I couldn't understand everything.
But Scott, isn't it possible that the universe became homogeneous, that things just became, I mean, I don't know, maximize entropy, so it started not
It's
being
possible you can break an egg and it will go back to an egg, but it's unlikely,
No,
right?
it's the opposite. I would say homogeneous is bigger entropy than non-homogeneous.
Yes.
So I would think that it might have started in specific places and then it became homogeneous.
But I guess that's not true. Well, I mean, you should Marisha answer, but I think inhomogeneities tend to grow in the universe, not decrease. If you have more, yeah.
No, I understand. It's a little counterintuitive, but I agree with you that usually happens.
So basically, so the onset of the radiation era, or the onset of a thermal bath, is when the inflaton field, well, based on the inflationary theories that explains why the universe explain actually the anisotropies, the seeds of the anisotropies of the CMB that allows for the how to say formation of structures and so on. So the inflaton field, let's say phi, goes to radiation. I'm calling gamma. So this is the onset of the thermal bath. At a temperature T. So basically, we will solve the evolution of the inflaton. So just applying this equation here for the inflaton field. Okay, it's a pressureless field, so the pressure term there is 0. So this is equal to, we can show from the definition of the collision term, we can show that this collision, the source term here, is minus the decay width of the inflaton times the energy density. Okay, and also the radiation that will be produced in this process will evolve like this. So just applying that equation for an ultra-relativistic species that we are calling, like, generically the radiation. So this would be plus the branching ratio of the inflaton going to radiation times the decay width and energy density of the inflaton field. Okay, so it's basically a transfer of energy from one sector to another sector. And we need to solve this coupled evolution. So from the first law of thermodynamics, we see that the entropy, the evolution of entropy is given as a function of this inflaton decay. So basically, we can equate this. Okay? And this is how we can see how the entropy increases with time because of this process of inflaton decay into radiation. So we can change variables to make this set of equations easier to solve numerically. So basically, we can work with the total number of inflaton fields, which is the number density, times the A cube. And this, since this is a non-relativistic species, this is just the energy density times the over the mass. Okay, and we have the we can call the total, the co-moving number of radiation as this. We can define like this. So the energy density times a to the 4. And why this is interesting is because we can solve this equation. We can write like this. So the change in the total number of inflaton fields will be only how they decay. And the co-moving number of radiation will change like this as well. Okay, so this is easy to understand how to, just if this is 0, then the total number doesn't change with time. And the same for radiation. And we can evolve these equations. Instead of time, we can evolve as a function of the scale factor. This is much easier to do. So basically, we can have, so this is the coupled equation, and we can have, for example, x equal to some mass scale or energy scale. In this case, we can choose the inflaton mass times the scale factor. Okay? So this is what we are going to solve. And now I will show the solution, the typical solution for these coupled equations of inflaton going to radiation. So basically, if we have here the co-moving numbers of inflaton and radiation in this y-axis, and here we have the scale factor. So basically, x proportional to the scale factor. We start just after inflation. We have a given number, total number of inflaton fields. So it's constant. At some point, they decay. So this is what this equation here is telling. We are losing the number of inflaton fields as they decay. And assuming that this is the production of radiation, so we start with no radiation in the beginning, and we increase the radiation content of the universe. So this is the solution of this second equation here. So we increase the number of radiation. At some point when the field decays away completely, the co-moving number of radiation levels off. So this is the starting point of the thermal bath. So basically this is defined as a reheating temperature. So this is the inflationary reheating. And the entropy, sorry?
What caused
The initial decays, you mean here?
Yeah. Why is so flat at the beginning?
I mean, it's just
It's just a logarithmic
it's not
scale.
effective enough. So it takes some time depending on the decay width.
Right, but what is causing that? The rho phi, no? Or the
Rho phi.
What determines the initial flatness, let's say? The initial.
I mean, this is just to say that we have, when it takes some time until the decay happens, is effective. So before that time that the decay is really effective, the lifetime of this particle,
Okay.
By that time they decay quite fast,
Okay.
exponentially, and this is the onset of the. So for the so this is the co-moving number of radiation here, and for the entropy, we start with no entropy. So this inflation comes to explain why. How is the entropy of the universe that high that we observe? So we can start with no entropy at all, and by the time that the inflaton field decays effectively, the entropy goes up. Okay, so this is the entropy here. And this is how we produce the entropy in the early universe. So this is the inflationary reheating. Okay. And, but it's possible that at some point in the evolution of the universe, a given field, this is possible in many beyond standard models, scenarios. A given field decouples from the thermal bath while ultra-relativistic. So basically, let's say, a given species, psi. So basically, if they decouple ultra-relativistic, by the time that they become non-relativistic, so the energy density of this field, as compared to the energy density of radiation, will be basically the mass of this field times the number density. So here we have the energy density of radiation. And basically, this is for a matter field. So this goes as T cube, while the radiation content goes with T to the 4. Okay? So basically, this is T to the minus 1. And in the case of no entropy production, like while the entropy production is not effective, then this increases with the energy, with the scale factor. So it is possible that at some point, the energy density of this field that decouple ultra-relativistic overcomes the energy density of radiation. So in this situation, let's say, here's the comoving number of the radiation. At some point, some different, let's use a different color. This other field goes, so this is the x, this variable there, and the number of psi. So it goes up. Should decrease. So, yes, sorry, I should have mentioned. So this is an unstable field. We cannot have a stable particle because otherwise it would be like a matter-dominated universe. But so if this is an unstable species that decouple ultra-relativistic, once they become non-relativistic, they can, in principle, overcome the energy density of the radiation. So this is an early matter domination just after inflation. Or it can happen anytime in the early universe. The standard cosmology assumes radiation domination just after the reheating until the point that matter content, so the dark matter, dominates the energy density. But it's possible that an unstable field dominates the energy density, so dominates the expansion of the universe for some period. And the duration of this period depends on the properties of this field. So basically the decay width of this field. So once this field, psi, decays, then it decays into radiation or something else. But if they decay into radiation, then the radiation content goes up again, and the entropy also goes up again. So this is a quite, quite possible scenario, and it's predicted in many beyond standard model theories. Okay, so this is what we call the intermediate reheating. Okay, not necessarily related to inflation. So why I'm calling this a reheating is because if we solve this equation for the temperature, so how the temperature goes with the scale factor, we can define the temperature from the definition of inflation, of entropy. Just at the definition of total entropy, we can define the temperature. So since we are solving for the entropy, we can find the solution for the temperature. And what we find is that the temperature of the thermal bath has a maximum value, and then it goes as a to the minus 3/8 while the inflaton dominates, for example, in this case of this scenario. Then at the reheating temperature, we have no entropy production, so when the radiation content is already established, and the temperature goes A2 minus 1. So during reheating, so during entropy production, the universe cools down slower than in a normal, in the phase without entropy production. Okay, so this is why we call reheating. It's not that the universe is heated up, but it's just, it cools down much more like slower. So basically, this affects the Hubble rate. So we have, no, let me write down there.
Sorry, Maria, I missed it. Can you just briefly explain why the temperature jumps up at the beginning before that epoch that you're calling reheating?
Yes, so here would be what we call the preheating, right? Like if we don't have a thermal bath, if it's not like, okay, so inflaton can decay into species, and it can take time until these particles thermalize. So this could be more complicated before that. But here we are just assuming that an instantaneous thermalization. So this is an approximation. But if the reaction rates are very fast, very strong, we can just start with, this could be a good approximation to that the universe, the radiation content thermalizes instantaneously. So this is what but this is just the solution of the differential equations.
Okay, thank you.
So just But things can be more complicated before that, before the establishment of the thermal bath. And this is an active field of research. So basically, the Hubble expansion rate, while we have radiation domination, is so basically it's proportional to the energy density of radiation, the square root of energy density, and this scales as a to the minus 4, so we have a to the minus 2, and if we don't have entropy production, then we can see that the relation between temperature and scale factor is just T goes as a to the minus 1, so we just have T squared. So this is the usual expansion rate for Hubble expansion rate for radiation domination. For matter domination, so non-relativistic matter domination, we have just the matter square root, and then this is just minus 3 over 2, and it goes as 3 over 2 if we don't have entropy production. Now, in the phase of entropy production, let's call like this, we have a matter domination. Okay, so we have the same thing like before. However, the relation between temperature and scale factor is different. So it's 3 to the over 8. So we have actually the Hubble rate is, the expansion of the universe is faster during this entropy production period. Okay, so dark matter can be produced during this epoch. So let me just write the general case here. So dark matter, I'm just defining as K, sky, dark matter production. During reheating. So we can have the number density of dark matter. We have this equation controlling the how the number of dark matter changes with time. So basically, we can have radiation produced in dark matter. So the collision term would be, we can define later, but it's just a generic thing. And we can also have dark matter being produced in front inflation. So we can have a branching fraction of dark matter and the inflaton decay, like this, and the evolution of inflaton is the same thing as before. And now radiation also, in principle, is affected by the dark matter production as well. So we have the production of radiation from the inflaton, minus, so we are losing radiation to produce dark matter, minus this, but now the source term that, inject energy into the dark matter bath, well, the dark matter sector. So radiation to dark matter. So this is the most general situation, and in some cases, it's very important to consider that. So now I can start talking about the second part of the talk. Which time is it? It's okay.
Can I ask
Sure.
a general question on this? After all, no, it's all phenomenological in the sense you don't have a model for the inflaton, those gammas, no, the decay width are just phenomenological numbers. So it's all about conservation of energy. You have some energy stored into inflaton, then it goes into
Radiation or dark matter.
and dark matter. So at the end of the day, you wipe out, no, the dependence on the initial condition, or
Yes.
is it still
Yes.
a dependence?
But at some point, so that everything depends on the reaction rate of dark matter. Basically, in some models, especially the models that depend a lot on temperature, so the temperature dependence is so high that the dark matter production finishes just as soon as we have a thermal bath at the maximum temperature of the universe. So we cannot decouple the evolution of the inflaton with the dark matter, to the dark matter evolution. In some models, these are the models that I studied.
No, but my question is really basic. So at the end of the day, you know, I have some amount of dark matter and some amount of radiation which is fixed by later observation. So how do I disentangle the different?
Because the final relic abundance of dark matter can highly depend on these scales, on the physics of the inflation.
Yeah, but anyway, it's fixed
Well,
by
after
observation.
observation.
The end point of dark matter is fixed.
Yes, but if the relic abundance depends on the temperature, it's different. We have another parameter to take into account in order to find the final abundance. But you're right, like we have the final abundance. So this is the only number that we have. But the way that this final abundance depends on the parameters of the model is what we need to take into account carefully. So it depends on the models. Of course, it depends on if we have any intermediate, reheating period and so on.
So you do reverse engineering on this parameter.
Yes, in order to constrain the parameter space with the correct relic density, we need to know how they depend on the parameter space.
Thanks.
So I have a question. So maybe I missed, but do you have an expression? So the reheating temperature only depends on the inflaton decay rate?
Yes.
Do you have an expression? Did you write an expression for the?
At some point I had this expression. I don't know if I have here in my notes, but yes, it depends on the physics of this field, this unstable field that is dominating the expansion.
So it only
I have in my
depends.
thesis like all
Okay,
the
so it only depends on the
all the
width
physics of this field that's
of the width
unstable.
of the inflaton,
Yes, and the mass.
or the partial width actually of
The
the
mass,
inflaton
yes.
to
But
massless
also, yeah,
particles.
yes, but also in the case of the inflationary reheating, we also have a dependence on the number after inflation, the total,
Right.
the initial yield.
And sorry, Nathan. And also, do you know what are the bounds on the reheating temperature that you get from cosmology?
Yeah,
Yeah.
this is interesting. I never went into details about this. I tried to, but well, I didn't work like exactly on this. But I know there are some constraints from the CMB measurements, like that we can use to constrain. But it's quite, we don't know the scale of reheating, so it could be as high as 10 to the 16 GeV and as low as 4 MeV because of Big Bang nucleosynthesis constraints. But yes, we don't know, and that's why it's important to take into account like more generically, like what can happen in the universe for the dark matter production. Because dark matter production quite necessarily needs to happen before BBN, before Big Bang nucleosynthesis. So before that, we don't have any phenomenological knowledge about the universe.
You need to ensure antimatter unbalance, and then low energy is very difficult.
Yes. You mean, yes, the asymmetry between
Yes.
matter and, which is another open problem, yes.
So I mean, so it's easier to send it to higher energy because at higher energy you have more unknowns.
Yes.
So if you set the reheating too low, then it's very difficult to tweak the known physics to get.
Yes, yes. And it's also very interesting to relate dark matter abundance with the generation of matter-to-matter asymmetry. It's possible in some models, and yeah. Okay.
I have a very naive question. After CMB, is it believed that dark matter abundance is constant?
Yes. Before, yeah, the dark matter relic abundance needs to be before the CMB to
Right,
grow
but-
structures.
But is it
in time.
essentially, I mean, is there experimental evidence? So as he said, I mean, right now we know what the dark matter abundance is now, supposedly.
Yes.
Do
More
we,
than 1/4.
is there evidence that it's been constant since the CMB? Can we say something about that
I think so because of structure
Observations?
formation.
from
I think so because of structure formation. So we need the dark matter. The cosmological need for dark matter is more like for structure formation. So we need
is more what? I didn't understand the phrase.
sorry, it's more because of structure formation.
Okay, yeah.
So we need a component, a matter component that clumps much before CMB.
I understand, but being constant is not the same as saying that it's not present. I'm just saying, do we believe it's constant? I mean,
But
is there evidence that it's constant, that it's not growing or shrinking or something like that? I mean, I don't know. You understand
Well,
my
the spectra
question?
of the CMB,
The percentage of dark matter in the universe, is that supposed to be constant since the CMB?
I think it's the,
Yes?
at least globally, the abundance don't change don't need to, cannot change before the CMB because globally the structures were formed. Of course, nature can be much more complex and we don't know about that. But the simplest explanation and also that fits the spectrum of the CMB is that globally the abundance of dark matter is already established before the CMB.
Okay, thanks.
So the relic abundance was already globally, like the bulk of the energy, abundance was established already before that. But yes, it's like locally, yeah.
Okay.
And also, like we expect to find the signals of dark matter from, for example, gamma rays. So dark matter is being missed, like, but just locally. So locally, things can happen. Dark matter can decay, but not globally. Yes.
Okay.
At least the bulk of dark matter is already fixed. So I don't know if I have time because it's already. Okay, yeah, I can run a little bit. Where is my? Okay. So So as I said that the dark matter relic density can be, how to say, defined like this. So we have the dark matter relic abundance here, so dark matter. And this is like today, so we can use this subscript 0. Today is non-relativistic, so we have the dark matter mass and the number density that we find after solving this equation, the Boltzmann fluid equation for the number density. So this is what we have here. And it is very convenient to define a co-moving abundance for dark matter that don't change with the scale factor. And let me write there. So the co-moving number, the co-moving yield of dark matter is defined as the number density of dark matter over the entropy density. And this is co-moving because for non-relativistic dark matter, we have, right, that we need that. We have a to the, it scales as a to the minus 3. And the entropy density also scales with a to the minus 3 if we have entropy conservation. Okay, so this is needed for that. But that's not necessarily the case. As I said, that we can have the dark matter production during reheating, during entropy production. So the entropy is not constant. And this is what we wrote a code to compute the dark matter evolution during an early matter domination. So our code is called EVO-EMD. And that's also can be used for dark matter freeze out, freeze in, or leptogenesis as well. So it's quite generic. And so basically, we have this this equation here for the dark matter production. And so we can write like the, I would just give some intermediate steps. So if we just replace the, instead of number density, we work with the yield, we can write like this. So this equation becomes like this. The yield of dark matter S plus the yield, the time variation of entropy, in the case that we have entropy production, like this. And I will give some intermediate steps. So we can write like this. So the variation of the yield. Now in terms of the scale factor, in AA. Oh, sorry. Then the variation of entropy with the scale factor, plus 3, plus this last term here. Now, we can define, I can do this here, we can define a parameter that quantifies this possibility of having entropy production. So this is the beta parameter that we call, defined as minus dln-A, dln-T. This is convenient because the rate, the reaction rate depends on temperature. So it's much better to solve the equation, the evolution of dark matter in terms of temperature. And also, we can define the way that the degrees of freedom changes with temperature. So we call this GS star. So it's 1 plus 130 dln GS over dln T. Okay, if we define these two things here, we can write the evolution, like the most general evolution of dark matter, with the possibility of entropy production as follows. So it's minus temperature, okay? So basically, if we have entropy production, this term here is 0. It's vanished. So this is the most general case. And I would just keep here. And let me talk about the collision term. What is there? So basically, as I said, this collision operator encodes all the possible interactions. So basically, we have like one. We have multi-particle states like X, something in the middle, and some multi-particle states Y. So we can have interactions going in both ways. And basically, I would just say the assumptions that we made for writing this the collision term. So basically, we assume that the occupation number is much. Sorry, these are the particles I and particles J, just for fixed notation. So the occupation numbers are much below 1. So this is a classical phase space, and this allows us to neglect any Boltzmann, any Bose enhancement or Fermi blocking. So this, the reaction rate will depend on the final state 1 plus minus F, but this will be approximately 1, so it's just Maxwell-Boltzmann. And we also assume like kinetic equilibrium. So this allows us to write the out of equilibrium distribution functions as proportional to the, equal to equilibrium density, equilibrium distribution. But this offset of equilibrium is quantified like this. So N, it's in equilibrium. So these are the assumptions. And we also assume CPT. So basically, because of the CPT theorem, we have the amplitude for one process, like X to Y, is equal to the amplitude for the conjugate Y state going to X, conjugate X. So these are the assumptions that simplifies the collision term. And in the end, we can write things quite simple. So basically, we have the reaction rate for process X to Y is equal to the product of all the initial states, the product of number densities over the equilibrium number density, and the reaction rate for X into Y. Minus, so this is for chi in the Y state. So we produce chi, the dark matter, and we lose dark matter in this term here. So J. So we have, again, like this. In this case, the Bragg reaction can be related to the reaction because of CPT, so we have this. So this is the most general case. And the possible initial conditions determine how the dark matter is established, the dark matter abundance is established. So let's say that all the particles different than dark matter are in equilibrium. So all the particles that are interacting with dark matter are in equilibrium. So we have this. And let's suppose like two possibilities for the initial condition of dark matter. So initial condition equal to equilibrium. So if dark matter is initially thermalized with the species that they interact with, we have the freeze out. So that means that we need to consider both production and annihilation. And if we have a negligible amount of dark matter in the beginning, and if dark matter never achieves equilibrium, so if this condition is always valid, then we have the freezing production. And then we don't have annihilation. So we can write, in the case of 1, 2, going to chi-chi, let's say, this reaction rate density for 1, 2 going to chi-chi is equal to the equilibrium density of dark matter, so the dark matter fields, states, in the annihilation cross-section. But we can also write the same reaction rate as in terms of the particles 1 and 2 distributions. And this is convenient for the freezing description. So in this case, we have the sigma V for production. Okay, so we have, let me write this here. So basically, the reaction rate density is, how to say, like we have two possibilities. We have annihilation, sigma V of annihilation, times number density of dark matter at equilibrium, minus the out of equilibrium, the out of equilibrium number density of dark matter. And this is the case of freeze out. And in the case of the freezing, we have the production annihilation and the equilibrium number density of particles 1 and 2 minus the out of equilibrium number density of dark matter. But in this case, as I said, this is much below the equilibrium distributions, the equilibrium number densities. So in the case of the freezing, we just have the production. Okay. So if we solve this equation for the freeze out, so the comoving yield in the case of the freeze out, it initially follows the equilibrium yield. So dark matter goes like this, and then we have the freeze out at some point when the universe expands faster than the rate of interaction. And in the case of the freezing, we have so the yield of dark matter, the comoving amount of dark matter, as a function of, this is a function of time, like a dark matter mass over temperature. And then, like, we have the equilibrium here. But as I said, in the case of the freezing, dark matter never reaches equilibrium, so the amount of the comoving amount of dark matter is always below the equilibrium. So we have this. So the dark matter production levels off, like finishes, when the yield is much below the equilibrium distribution. So if we have early matter domination, in the case of the freeze out, we need dark matter to decouple much before, because we have the dilution. So to compensate the dilution of dark matter after a period of reheating, the dark matter must interact more weakly with the thermal bath. And in the case of the freezing, we have the opposite situation. So we just have, to overcome the production, dark matter needs to interact more strongly. So that's the main idea. So I can stop here. Thank you.
I'm not an expert. Could you just summarize a bit what was a well-established textbook stuff and what was the stuff that you guys did that was more new?
Okay, the part of the cosmology is very standard. Even the inflationary reheating and reheating, like intermediate reheating and so on. What we have done was to develop codes, numerical codes, for the dark matter production during reheating, because in some cases, I didn't have time to show, but in some cases, basically when the temperature dependence of the rates of this chi are very high, the dark matter is produced just before the establishment of the thermal bath, like just before this, so in this period here. And this is not, how to say, we don't have public codes for that. And we have done a public code. We have published a code about this in any particular model, in particle physics model. GitHub, yes. And also, we developed codes for freezing production as well, in the general case. But this equation here, I don't have it more. Like the general equation for, in terms of the beta parameter, we developed to have like one integral differential equation to solve for the general case. So this is the new part.
But these codes are based on the equation you wrote today? Or
Yes, yes. Yeah, the equation that I wrote, I should have kept it. But the equation that I wrote for like the most general, in terms of the beta and so on, that this parameter is what we wrote for in the EVO EMD code. So
I think I'm missing something basic, because I mean those equations were very simple differential equations, right? You don't need code for that. Probably there's something hidden inside inside this scattering
there are
whatever.
integrals inside this R chi.
So what you did is hidden inside this R chi that you did not show, right?
But it's basically, yeah, but it's
Okay.
basically.
So can you say a few words about R chi? What is R chi?
So R chi, basically I have here, right? So it depends on the kind of process that we have. So if we have a 2 to 2 process, it's basically the cross section times velocity, so the rate of interaction. And if we have like 1 to 2, we have the decay width and so on. But it can be like more complicated than that. We can have 2 to 3 and so on, like processes. There are some.
I think there's probably something basic that I'm not following. So that R will involve the same variables on the left-hand side of the differential equation, right? So you had some FKs and so on, or NKs. And then the R, the variables inside are the same, but integrations of those things, it's a bit non-local. Can you just write an example of some term inside R so we have an idea what's the complexity?
Well, for 2 to 2 is just here, for example, and the cross-section. But the cross-section can have resonances and so on.
These ends are exactly the ends that you solve, okay.
Yes, yes.
So I'm still a bit puzzled. So what is challenging in this business? It's the fact that the cross sections, you need to fit them, or I'm still a bit confused why I can't just solve the differential equation.
So the public codes are only valid for no entropy production. So we have an extra term in the evolution of the equation of, let me see if I have here, based on the n dot plus 3hn equal to r. If we write this in terms of the co-moving yield, we have an extra term allowing for entropy production. So it's more generic. And we can solve like very fast by splitting the Hubble rate. It's not that difficult, but it was never done before. So we have a code that splits the Hubble rate and computes the abundance of dark matter correctly in these different cases, different possibilities. So in our code, we can just choose the temperatures, so the reheat temperature and the initial temperature that this field starts dominating. And so this controls the duration of this early matter domination, and we solve this equation.
Can you elaborate a bit more about how right now the code is organized. So I don't know, do you have a wrapper? I mean, suppose that I'm a user and I want to use. Is there that, I don't know, there is a wrapper and then under the hood is running in another language or something like that?
Yes, the code is written in C++.
Okay.
And, and we use multidimensional integration, the Cuba, it's called Cuba.
Okay.
So then we can handle like the most general, how to say, processes.
Okay.
Not just 2 to 2 or 1 to 2. Right now, it's not very user-friendly.
Okay, so you don't have yet an interface that I can arrive with Python
We do, but it's not like very straightforward.
Okay, I see. So it's still for specialists,
so we have,
let's say.
Not much. Like we need to implement the amplitudes, the squared amplitudes for the process.
Okay.
And basically say which particles are in equilibrium or not, and so on, and that's it.
Okay.
But
and
yes, you have to calculate the.
Yeah.
It's not like you. At this point.
It's not yet a black box that I.
No.
Okay.
But we want to, at some point, it's not my focus anymore right now, like immediate focus, but I want to do use the final rules outputs to use this code more easily.
And are you planning to, as I was saying, to realize also wrappers such that I can arrive with another language? This is often the case. Like Python never run its own code. It's always something under the hood. And that, are you?
Yes, I found that C++ is better for this kind of problems because we can have this solution of integral differential equations more.
No, yeah, I don't deny that.
Yeah,
I'm saying if
yes.
you are preparing an interface that put the two languages in communication such that, suppose that I've...
You mean like a Python and C++?
Yeah, like I can call from outside, this is what a wrapper does. You call from outside, from another language, you call a routine that is actually running.
At some point it would be nice to have that.
Yeah.
I'm interested in discussing.
I mean, Mathematica, Python, they are always like that. They never run their own code, right? They always call something else. Yeah, okay, thanks.
Okay, so let's thank Maira again. So the people who want to go to lunch.